Hello, in this video, let's put some numbers and try to understand how to model the delay in an inverter. So we're looking at one of the most fundamental design constraints, which is the delay of the gate. So when you design an inverter or any digital gate, this is one of the constraints which weighs in on the design. Obviously, this is in consideration with other constraints such as noise margin, inversion threshold, silicon area, power dissipation, etc. So, what is the goal? Our goal is to determine the channel bits of the PMOS and the NMOS that satisfy a given timing constraint. So, now let's first look at a generic case. So, at any given voltage on the input, the PMOS and NMOS in the most generic case will have some current flowing through. And as the voltage at the input changes from 0 to VDD, the relative drive strength of the PMOS reduces and the relative drive strength of the NMOS increases. And that leads to a discharge of the capacitor. So at any point somewhere where Vin is in between 0 and VDD, in a most generic case, there might be a PMOS current and there might be an NMOS current, which means that there is, depending on whether the capacitor is charging or discharging, there either might be a current flowing into the capacitor or a current flowing out of the load capacitance, right? And current flows into the load capacitor when the PMOS current is larger than the NMOS current, and current flows out of the load capacitor when the NMOS current is larger than the PMOS current. So at any point of time, if I want to calculate the charge up current of the capacitor, why do I need to do this? Because this current, this IC, is the current that is going to charge up the capacitor, and indeed that is what we need to find the delay of the gate, because this charge up of this capacitor eventually leads to the output either falling or rising, which leads to an estimate on the propagation delay. So at any point of time, the current in the capacitor is given by a difference in the two currents of the transistors. And based on the polarity, we either say the capacitor is charging up or discharging. So if I want to find how the output voltage varies as a function of time, then I can basically write the charge up equation of the capacitor, which is C dV by dt, is the charge up current, and that is given by IDP minus IDNP, right? So this is a very generic case of finding the delay in a gate. Basically, as Vin changes as a function of time, it is going to change the relative values of the currents, and hence the charge up or the discharge of the capacitor current changes, causing a change in the output voltage. So this is the first principles analysis, if you will, to calculate the delay in any gate, and in our case in the inverter. Now let's take a step back and think about the load capacitance in the gate. So the load capacitance in the gate is essentially made up of two components. One is the intrinsic component, that is, this capacitance is, some of it is caused due to the capacitance of the drain of the PMOS and the NMOS, and the CGD of the N and the CGD of the P. Right? So there is a component of this capacitance which comes from the transistors used to build the inverter, and this is the intrinsic component of the capacitor. The extrinsic component of this capacitor is determined by the wiring capacitance at this node. So this, suppose I've connected an interconnect or a wire to this node, the capacitance of that wire contributes to this load capacitance. Also, if I've connected multiple gates to the output of this gate, then the input capacitances of all those gates essentially fall as a part of the capacitance at the node, and this is known as a fanout capacitance. Now let's take a look at the transistor. So in a transistor, if you look at the top down view of the transistor, this is your diffusion, this is your poly, right? So in our digital circuits, we keep our gate length to be as narrow as possible. That way we can get the largest drive current. Now what happens if I increase the width of the transistor? If I increase the width of the transistor, what I see is that all my capacitors associated with this transistor will also increase. Why is that? The gate to source and the gate to drain capacitance increase because the area of the drain increases. Similarly, the drain to body capacitance of this PN junction diode is also going to increase because of the increase in the area of this junction. Why am I thinking about this? Remember, if I want to speed up the circuit, when I want to speed up the circuit, one easy way to speed up the circuit is if I increase the size of these transistors, right? So if I make this transistor W larger, then for the same voltage, I can pull lot more current through the transistor. And so I can trade off speed with area in such a case, right? So while the transistors will be larger, I'd be able to make the inverter switch faster. Not as easy as it seems to be because of the fact that some of the output load is also related to this internal transistors, right? So if I think about C out can be thought of as multiple components. The first four components are the transistor components. So you have the CGD of the NMOS, the CGD of the PMOS. Both of these are going to be dependent on the respective widths of the transistors. Similarly, you have the drain to substrate capacitances of the PMOS and the NMOS. Those are also going to be dependent on their respective widths. And then in addition, you have the interconnect capacitance or the wiring capacitance, and you have the capacitance of the next stage or the fanout capacitance. So you see that these transistor capacitances are proportional to the width of the transistors. Those are built in the inverter, whereas the wiring capacitance and the fanout capacitance are independent of the size of the inverter. So to a very simple model for C out or the load capacitance, I can talk about the C out capacitance as some component which is not dependent on Wn and Wp, and then I have two components, one dependent on the width of the NMOS and one dependent on the width of the PMOS. Now since all these capacitances are area dominated, they just come up as linear relations to W. So what you see is that the capacitances increase to first order linearly with the width of the NMOS and with the width of the PMOS. So now let's assume that V in transitions abruptly to VDD, which means that we have a current which is going to flow through the NMOS and that is going to essentially discharge the C load. So if I think about the output capacitance is going to be discharged through the NMOS, and the NMOS pulls the output voltage from VDD to VDD by 2, and that is what we define as the delay, which is from VDD to V50%, in which case is VDD by 2. Now if I assume that the NMOS is in saturation during this entire region, that means the NMOS current is going to be constant. Then I can very simply write my delay as C out into VDD minus V50 by IDN. Now this is the saturation current of the NMOS, and using the simple square law model, this saturation current is going to be independent of V out. So it looks as if this capacitor is being discharged by a current source. So for the NMOS and saturation, let's plug in the numbers. IDN is half Kn prime Wn by Ln VDD minus Vtn the whole squared, gives us TPHL, or that is the propagation delay for the falling transitions, the output, as C out Ln divided by Kn into Wn VDD by VDD minus Vtn the whole square. So here is what you expect. You expect that the falling delay basically will reduce if I increase the width of the NMOS, right? Assuming that C out is independent of W. Now, similarly, if I use the same argument to find the rising delay at the output, the rising delay of the output comes from the PMOS. And again, if I assume that the PMOS is in saturation as the output rises from 0 to VDD by 2, I can write this as the shortcut expression for my rising delay. So you see in both these cases, you have this 1 by W dependence on the delays. Now C out, we know, in reality has the interconnect and fan out capacitance here, but it has two other components which are dependent on the widths of the NMOS and the PMOS, right? And so if I plug that in, what's going to happen to this expression? That the falling and the rising delays, I replace my C out with this expression which is a function of both Wn and Wp. And so I get an interesting expression that the falling and the rising delays are related to some technology parameter, and then they fall in this format, which is a function of Wn, a function of Wp, and a function of the ratio of Wp and Wn. So now, basically, if you look at this, now let's try and understand what happens to this delay if I increase the transistor widths. So suppose there is no area constraint for my inverter, then I can imagine, then I can make the inverter switch very fast by increasing the widths of the PMOS and the NMOS, or in other words, by making the drive currents of both the PMOS and NMOS very large, right? So here is the expression which is derived for the falling delay and the rising delays. What we'll do now is, let's consider what happens to these expressions. Suppose I keep increasing W's towards infinity. And so what happens here is, as Wn tends to infinity, that is, if I make the NMOS as large as I can, eventually the falling delay is not going to zero, but it's trending towards a constant, right? And this constant relates to technology parameters. Similarly, if you look at the rising delay of the inverter, the rising delay, if I make the size of the PMOS very large, even in that case, I'm not going to get the rising delay to be zero, but I'm going to get the rising delay converge to a finite value, which is again technology driven. So the point I'm trying to make here is that in an inverter, when you increase the width of the transistors, or if you make the NMOS and PMOS large, because of the fact that the inverters have a self-loading happening, that is, capacitive load at the inverter output has a component that consists of the NMOS and the PMOS, which constitute the inverter, the delay through the inverter is never going to go to zero. It is going to hit a minimum, and this minimum is a technology driven parameter, is independent of the wiring capacitance and the gate capacitance. So another point to note is that, suppose you have a transistor, you have an inverter which is driving a load which is purely interconnect driven. That is, if I assume that an inverter has a load which is where the interconnect capacitance is much larger than the device capacitance, then by changing the values of the W's of the N and P, I can reduce the delay of the inverter. But I cannot reduce the delay of the inverter below this limit. So this is the limit of the inverter delay in a given technology. So let's look at how to mathematically put it all together. Suppose you want to actually go through the exercise of solving for the delay for a given inverter circuit, right? So let's assume that I've taken a specific case. Let's assume I want to find the falling delay at the output in this particular inverter, right? So I have again applied a step input from 0 to VDD. I want to know how Vout falls. So again, here I'm going to look at the NMOS current, because there is no PMOS current since the input has gone to VDD. I want to measure how long does it take for the output to fall from VDD to VDD by 2. So the NMOS, as we know, starts off at being in saturation and eventually moves out of saturation into the triode region. So at time t equal to 0, I know that VGS is equal to VDD and VDS is also equal to VDD. So the NMOS starts off in saturation. And then if I think about this as a velocity saturated device, then I can write my IDS in this format. And here you see that the IDS is independent of Vout, right? So for the first initial part of the discharge, the current stays a constant. And how long does this current stay a constant? It stays a constant until the transistor steps out of saturation. And when does that happen? That happens when Vout falls below the VD saturation, and the VD sat is given by this expression, which is VDD minus VTN tempered by the LE sat expression, right? Suppose we were using square law in this case, then I would have just written VD sat as VDD minus VTN. Now when Vout falls further, I basically find that the current in the transistor is no longer independent of Vout, but rather is dependent by Vout and is given by this expression, which is the expression for the current in a transistor that is velocity saturated in the triode region. So how do I find the delay in such a case? So again, start with the basics. This NMOS current is the discharge current of this capacitor. So initially this capacitor was charged up to VDD, and then this capacitor is eventually discharging through this NMOS. So the NMOS current at any point of time can be written as minus C out into dV out by dt, which is the discharge current of the capacitor. Rearrange the equation. What you get is integral 0 to TPHL of dt can be written as minus C out integral VDD to VDD by 2. So over the time from 0 to TPHL, the output voltage goes from VDD to VDD by 2, dV out by IDS, and this IDS is a function of V out. So this is now a matter of splitting the integral into two parts, one which goes from VDD to VD sat and the other from VD sat to VDD by 2. In this case, the current is a constant, so this integral can be evaluated very simply. Here you'll have an expression in the denominator which is a function of V out, and then you'll have to use numerical or partial fractions method to evaluate this integral. And so I can essentially write my falling delay as C out into VDD minus VD sat by ID sat. So this is the initial part of the falling delay where the current is constant. And then I have to evaluate this integral, which is the delay required for the voltage to drop from VD sat at the output to VDD by 2. So typically when we make transistors or when we make chips, we always want to measure the inverter delay on the chip. Normally the smallest inverter is drawn because the smallest inverter or the inverter with the smallest transistor sizes will have the smallest delay. And this delay is a figure of merit for a technology. So if I look at the inverter with the smallest area, its delay is a figure of merit, and it's a good predictor for digital system delays in that particular technology. So we use what is known as a ring oscillator to measure the delays. And what is a ring oscillator? A ring oscillator is made up of an odd number of inverters, right? And so essentially it's an unstable system. So what you see is that as the inverter gets powered, eventually it flips over, and what you see is that the ring oscillator oscillates. So every node in the ring oscillator oscillates between 0 and 1. Okay? So let's look at the profiles of the various voltages in the ring oscillator. So here I have 5 inverters A, B, C, D, E connected in series with the output of E shorted to the input of 1. So let's assume this is the profile of V1. Right? So let's assume V1 initially switches at this point from 0 to 1. When V1 switches from 0 to 1, V2, which was high, will switch from 1 to 0, right? And so V2 will switch from 1 to 0 and after a certain delay, and that is going to be the falling delay of this inverter A. Now as V2 switches from 1 to 0, V3 switches back from 0 to 1. So V3 switches back from 0 to 1, and so now we have a rising delay from V2 to V3. Again, as V3 switches from 0 to 1, V4 switches from 1 to 0. So I need to now worry about the falling delay of inverter C, and the output V4 falls. Now because the output 4 falls, output 5 is going to rise, and output 5 is going to rise, and it's given by the rising delay of inverter D. Now as 5 rises, you're now going to have the output of E fall, which is this value of V1. So you see that as V1 goes from 0 to 1, eventually the output of E pushes V1 to fall back to 0. And so again the 0 now propagates. So because this falls to 0, V2 rises to 1, V3 falls, V4 rises to 1, V5 falls. And because V5 falls, V1 rises up to 1 again, and the cycle repeats itself. So you see that every node here will be with the same frequency and duty cycle. So what you see here is that every node here, right, has the same frequency for the oscillation and the same duty cycle. What you see is that each of them, however, differ with a certain phase margin, if you will, right? So if I want to find out the time over which the signal V1 is high, the time signal V1 is high can be calculated by calculating the individual delays which we just looked at. So we have the falling delay of A, the rising delay of B, falling delay of C, rising delay of D, and the falling delay of E. So that is going to be the time when signal V1 is high. Similarly, when signal V1 is low, I can talk about the rising delay of A, falling delay of B, rising C, falling D, rising E. So you say both the high and low are complements of each other, right? So by measuring, so if I create this ring oscillator on my test chip, and when I power the ring oscillator, when I power this ring oscillator, I'm going to get oscillations at every node. And by measuring the frequency and the duty cycle of this waveform, I can individually predict the rising and the falling delays. For example, suppose I assume that all these have similar rising and falling delays, that is, if they have the same layout, then essentially my T high can be written as 3 times falling delay plus 2 times rising delay. My T low is on the other hand written as 3 times falling delay plus 2 times rising delay. So by measuring the frequency and the duty cycle, I can extract the rising and the falling delays of the inverter. So this is a very common structure we normally place on test chips, and this is done to evaluate our silicon to spice. So when we want to evaluate our spice models, when we want to test silicon, when we want to build models for silicon, one of the first test chips in the technology typically has ring oscillators. So to conclude, by nature of the design, the inverter delay is a finite quantity. So it is not possible in digital circuits, the way CMOS is constructed, to have a delay of an inverter to be zero. The delay is going to be limited by the technology, and this is because of the way the CMOS inverter is constructed, in that the load of the inverter is a part of the load of the inverter is determined by the transistors which are used to build the inverter. So inverter circuits may be optimized separately by identifying the kind of the capacitive load that they have. So suppose you find out that a certain inverter has a load which is very interconnect dominated, then you can try reducing its delay by increasing the size of the transistors. There is a limited gain you'll get by increasing the size of the transistors, because beyond a certain point, the delay is not going to fall as much as you expect. Finally, when we want to measure delays, we normally use what are known as ring oscillators, which we place on test chips, and these give us a good measure of the inverter, and it also gives us a good metric to use for all delays when we want to think about large scale digital systems.